All right, so hi, welcome to today. We are going to today start with some review, and then well actually the whole day's review. We're going to review everything we did from Friday, so we're 2 days on this one. So we'll go over what we did on Friday again. So anywho, this was from last chapter. We had a whole chapter on quadratic functions primarily, and solving for the x-intercepts and the y-intercept and the vertex and all sorts of stuff. So remember, at the x-intercept, what do we know about y?
0.
Good. So it's 0 and 0. And so what is going to be the x value that makes this equation true when y is 0? So put a 0 in for y and solve this. I'm going to solve it by factoring because I noticed this factors, and you really do have to be proficient at factoring in order to move through the rest of this course or any other kind of Algebra 3 or pre-calc. So anyways, this would be plus 7 minus 3, I believe, right? Okay. The two values that make that true are going to be then negative 7 or positive 3. So those are going to be my x-intercepts. So I have negative 7 and 3. Okay, my y-intercept, what do we know is true about x at the y-intercept?
0.
X is 0, so put 0 in for x and we get a negative 21 for y, so there's another point. So I have my y-intercept. I got two x-intercepts. Let's make a little graph of this. Why don't we make a little graph of this, huh? Okay, let's go like this. I'm going to make it kind of bottom heavy. It's going to have a x-intercept of negative 7. I'm just eyeballing it here. So negative 7 there. Let's make 3 right about there. Okay. Y-intercept is negative 21, so that's going to be like down here. I don't know, probably like, doesn't have to be perfect. Now where is my vertex? Well, the vertex is going to be located halfway between any 2 points that are on the same y level, I guess you could say the same height. And the concept here with this, I'll just draw a little parabola. If I had 2 points that have the same y value there, the vertex is halfway between those two. If I pick these 2 points that have the same y value there, the vertex would be halfway between those two. It's the midpoint of any 2 points on the parabola. Since it's symmetrical, it's the midpoint of that. So you just basically finding the midpoint, which would be the average of those two x values. It's like the midpoint formula. All right, so here we want to find the midpoint of those two values, which is negative 7 or 3. So if I take negative 7 and I add 3 to it and I divide by 2, I'm going to get negative 4 over 2 is negative 2, right? So there's like an axis of symmetry that comes through here at the x value negative 2. Right, so x equals negative 2 is my axis of symmetry. That's also my x value of my vertex. So now if I put negative 2 in to the function and I evaluate for y, I'm going to get 5 times negative 5, which is negative 25. And that seems to make sense because I have my y-intercept down there anyways, so now I know my vertex. So now I can just make a nifty little sketch through here. Dave, you like that word nifty?
I do.
Yeah.
Big fan.
Big fan. So there we got our nifty little parabola with the x-intercepts there, my y-intercept there, and my vertex there. Pretty neat. All right, so that's kind of a lot of the stuff we did last semester, or not semester, last chapter. In this chapter, we're doing things that are similar, but we're having like higher degree polynomials. So the factoring is going to be a little more involved. So let's review what we did last time we met. Last time we met, one thing we were going to need to be able to determine is if a binomial is a factor of a higher degree polynomial. So let's say x minus 1. Is that a factor of x squared plus 6x minus 4? One way we can check this is by using synthetic division. Okay, if we put whatever makes that 0, which is 1, in the little box, run our synthetic division. 1 and 6 and -4. I didn't skip any. And if I do this and I determine that the remainder is 0, then my solution or my conclusion is that it is a factor. So pull that one down. I always start it out, pull that one down. 1 times 1 is 1. Add 1 to 6, I get 7. 7 times 1 is 7. Add those, I get 3. Uh-oh. My remainder is 3. So what does that mean? It does not divide evenly. And so my conclusion now, since I have a remainder is not equal to 0, is that x minus 1 is snot a whoops, I wrote it. Is snot a factor. That would be in honor of Uncle Jerry. He would joke like fun stuff like that, you know, like everyone's got an uncle like that, right?
Yeah.
A funny one.
My Uncle Jerry.
You have an Uncle Jerry? Oh yeah. I bet he's a beaut. Okay, so not a fact. It's not a factor. All right, this next one, same concept, but there's a little bit of a twist here. This is 2x plus 8. So what goes in the box is whatever makes that 0, which is a -4. All right, now I'm going to use my synthetic division. I got to be a little careful. My quartic term is 2. So 4th degree is 2. My 3rd degree, the next one smaller, is 8. And now I got my 2nd degree, or my quadratic term, which I'm missing, so I have to put a 0 in. And then I have my linear term is 2 and my constant term is 8, so be careful on that. If you're missing any terms, have to put that 0 placeholder in there. Bring the first one down, 2, -4 times 2 is -8, -8 plus 8 is 0, -4 times 0 is 0, 0 plus 0 is 0, -4 times 0 is 0, 2 plus 0 is 2, -4 times 2 is -8, haha! 0 is my remainder. So because I have a 0 remainder, that's 2x plus 8, it is a factor. So the conclusion now is that, lo and behold, 2x plus 8 is a factor. I was just writing the test, and this is a question that we ask you. Is basically, hey, is this linear binomial a factor? And then you got to just do exactly what we did just now. And then if the remainder is 0, you'd say, yes, it's a factor because the remainder is 0. BC rem equal 0. Make sense? Any questions on that? All right, moving forward. Next thing we talked about, Next thing we talked about was factoring by grouping. So this is a special fun little factoring strategy that might work if you have 4 terms that is a cubic. So in this case we have a cubic 4-term polynomial. And so let's see if this puppy groups. All right, so we group the first 2, we group the second 2, factor out a common term in each one of those grouping pairs. This one would be an x squared factored out, left with x plus 4. Over here, I factor out a 2. What's left is an x plus 4. Haha! It does group. You know how I know? You know why I know? Because that right there is there's the same binomial, common binomial factor. Yeah, that is pretty neat there. So now each one of those binomial factors you can factor out. It's like a binomial factor in a binomial. It's like a binomial within a binomial. Whoa. Yeah. For the ones that we do, it does, but it maybe, I was thinking about this earlier, and we don't do any like this, but if it had like to the 6th power, and then to the 4th power, and then to the 2nd power, and then a constant, that might work too, you know? I don't know. Maybe play around with that and see if it works in some of my free time. Okay, moving on. Oh, I gotta finish this problem, silly. So now factor out an x plus 4, right? So that gets factored out, so that's now out in front. And what I had left in there was x squared plus 2. Sometimes this x squared plus 2 stuff is like the difference of squares and you can continue, but this one doesn't, so I just put a ka-chow on that because I'm all done. So that one's fully factored. Let's try one more. Group the first two. Be careful when you group not to put the parenthesis to the in between that sign and the number, right? Like if you put it right there, that would be bad. You'd be changing the problem. So don't put it there. Put it to the left of the sign. So we group like that. First thing here, we factor out a 2a squared. So now we get a 2a squared times what? 5a plus 2. And then here I factor out, this one's a little funky. Factor out a -1 because I want to get those things to match. What if I factored out a -1? Then I would get 5a plus 2. Haha, lo and behold. I keep saying haha today. There it is. Factor that out. A good Canadian. Factor it out. Okay. Now we have, wonder if we're going to get any Canucks watching these videos on YouTube. Probably not. 2a squared minus 1. Like that. 2a squared minus 1, not the difference of squares or anything crazy, so I just ka-chow. That's done. Fully factored. Some students have this, they wonder about this bugs them a little bit. This next page says like, how come we don't write it as like the stuff squared? Because you're pulling two of them out. Like back here, I think I talked about this on Friday in here actually, someone asked. But the question, or the thing that some people wonder is like, how come this is not 5a squared? I mean, you pulled two of those 5a plus 2's out. Wait a minute, I saw a mistake there. That's a plus. How come it's not 5a plus 2 squared? You pulled two of them out. Okay, how come it's not? All right, I'm going to try to show you a simpler example and see if you have an aha moment. So like, let's say we have 5x squared plus 25x. Okay, and I'm factoring that. Can I factor out any common terms there? Yeah, so you probably don't have any problem realizing that that's the same as 5x times x plus 5. Are you okay with that?
Yeah.
It's like a reverse distribute, right? Factor out a common term. If I rewrite this as 5x times x plus 5x times 5, that's the same, right, as what I had above. I'm deconstructing it a little bit. You agree? Okay, and now essentially what I just did was I factored out a 5x from each term, right? So it's not like I have two of them because I'm undistributing it. So 5x times what's left is x plus 5. You know, it's not like I have 5x squared when I pull it out. So that's the same thing as what we were doing over here, is we're taking 5a plus 2 out from each term. So it shouldn't be 5a plus 2 squared, right? It's not. It's not squared. There's just one little 5a. Oh, it's all gone now. All right, so hopefully that helped a little bit. Let's jump ahead. Let's keep this train moving. Talk about the... we don't need any more of those, do we? Now let's do this one. Is a little weird. I'll go fast on this one so you can do slow motion on YouTube. All right, this one each has a factor of 3, so I'm going to take a 3 out of each one like that. Boom, like that. And there we got x squared minus x cubed minus x squared minus, what is this, 4x plus 4. Okay, so you might be able to factor out a common term. No problem. You can always do that, and you should always do that. Sometimes I forget to do that. Okay, now the rest of this stuff groups. Look at, I can group these two, and lo and behold, I will have something that factors by grouping here. Take an x squared out of there, so I got x squared times x minus 1, and then over here I have a minus 4 times x minus 1, like that. Okay, take that common term, that x minus 1 that makes the grouping work. If grouping won't work if these two terms aren't the same like this, You don't get a common binomial term. So now what I have left is 3 times x minus 1 like that, and then what's left over was x squared minus 4. Can I do anything else? I can go a little further, right? Because this right here is the difference of squares. So I can take that difference of squares right there, take it one little step further, and this is 3 times x minus 1 times x plus 2 times x minus 2. So you might have a little bit of a difference of squares pop in before you totally ka-chow on that and finish the question up. Okay? So you got to be able to use all the different strategies and identities and stuff that we've been learning along the way here. Okay, the last thing we talked about was the sum and difference of cubes. And the identities I gave you, I'll give you, I'm not going to make you memorize those. So we have a cubed plus b cubed identity. This one's the difference of squares, so this one's going to follow the difference of squares identity. A cubed minus b cubed is equal to a minus b times a squared plus ab plus b squared. Okay, as long as you have the difference of two perfect cubes, which we do here, this will factor using this identity. So what is my cube root of z cubed? That's z, or like they say in Australia, z. And then 27, what's the cube root of 27? By the way, over here on the whiteboard, I put the first 5 perfect cubes, just 1, 8, 27, 64, 125, right? So 27 is 3 times 3 times 3. So the cube root of 27 is 3. So now everywhere you see an A, you put a Z, and everywhere you see a B, you put a 3. So it's going to be Z minus 3 times Z squared plus 3Z plus 9. Okay, nothing more to do with that. Some people wonder if you can unfoil that quadratic trinomial, and you can't. You're not going to be able to unfoil that when you use a sum or difference of cubes identity. This is always a DNF UQF situation. Does not factor use quadratic formula if you're solving. All right. Here's the sum of cubes. So sum of cubes is going to be a cubed plus b cubed equals a plus b like that times a squared minus ab plus b squared. What's the cube root of a cubed? It's kind of funny, that's just a. Cube root of 64, 4. Everywhere you see an a, you put an a. Everywhere you see a b, you put a 4. A plus 4 times a squared minus 4a plus 16. Nothing you can do with that because you're not going to be able to unfoil that trinomial, so that's straight up ka-chow. Neat, eh? All right, couple more harder difference of cubes, and then we'll wrap this up. So this top one, you look at those and you're like, well, those aren't perfect cubes. Yeah, but you can factor out a common term. Factor out a common term and watch what happens. I dare you. Okay, take a 3y out, and now look at 8y cubed minus 1. Told you there'd be a difference of cubes in there. I told you. You're probably going to go home and eat some lefse for a snack, aren't you? So take 3y. Let's take the difference of cubes here. 2y minus 1. And this is a little tricky part here because 2y squared is going to be 4y squared. All right, and that's going to be plus 2y plus 1. This probably bugs people when I don't write the identity. So this would be like a minus b times a squared plus ab plus b squared. So the a was 2y and the b was 1. And so everywhere I saw an a, I put a 2y in. And this part right here is a part where students make a mistake. They just put, a lot of times they just put 2y squared in there. You gotta square the 2y times the 2y and get a 4. Whew. All right, Kachow, last one. Flying here. This one is actually the difference of two cubes. It's just a little disguised in there because s to the 6th is a perfect cube. Okay, so what would the cube root of s to the 6th be? S squared, good. And then the cube root of 1? 1. Someone asked me earlier today, they said, well, wouldn't it be like the cube root of a -1 be a -1 for b? Don't get involved with the negatives for a and b. Just follow the signs in the identity. So just keep a as a positive and b as a positive and follow the signs in the identity, or the formula, I guess you might call it. So now we have a minus b times a squared plus ab plus b squared. Follow that. So a is going to be s squared. So s squared minus 1. Ooh, I know what that is. And then s squared squared is s to the 4th. Plus s squared times 1 is s squared. Plus 1 squared is 1. So you end up with that. Now this is kind of funny because look at what I have right there. Difference of squares. Hey-oh. S plus 1 times s minus 1 times s to the 4th plus s squared plus 1. That's fully factored. Lightning McQueen would totally put a ka-chow on that. Woo-hoo. Can you up? Add the s to the 4th plus the s squared? Nope, you can't do that. Good question. You can't do that. They're not like terms. It's kind of funny. If I were to put like x to the 4th plus x squared, would you think to add those? You can't add those together, can you? No, you can't. You can multiply them. Watch this. Hold on. You can't add them. Now watch. Let me do one more thing. X squared plus 4x plus 3 equals 0, right? You can't add x squared plus 4x, can you? They're not like terms. So you can't, just like these, they're not like terms. They don't have the same variable part. You can't add them together. I appreciate that little nugget of information there because, yeah, like, oh, can you add those together? Students might be thinking that. You can't. They're not like terms. All right, that was a long one today, 23 minutes. And what was it? 68, right? All right, here we go. 20 push-ups or not.